I'd like to start by introducing myself. My name is Francesco Degrassi. I'm 44 years old. I work with the software, both developing and operating it. And I definitely like PostgreSQL. Having worked in the field for 20 years now, it's one of the few software solutions platform things that I've learned to use that are still as relevant today as they were 20 years ago. And that, especially if you are involved in the operation of software platforms, it's something that you start to really value. To have something that is reliable, dependable, that you can be confident about how it is going to work, how it's going to respond to the loads that you put on it. The ability to have a lot of support about Postgres. Most realities that operate with software platforms use Postgres. It's provided by major cloud providers as a managed service. It has mature community. For me, it's also important that it is open source, since as a software developer first, being able to peek under the surface, understand how it works and so on, becomes something that is really valuable. But today, I'm not going to talk much about why Postgres is so valuable per se, but I'll focus on the extensibility of Postgres. The ability to modify its behavior, extend its behavior, make it do things that it was not originally meant to do. And this is something that really sets it apart from the competition, from my point of view. Why should you care about the extensibility of Postgres? Why it is a critical factor? Well, first of all, because it allows us to improve the expressiveness of the data access code that we write. So if we're dealing with our domain objects, we want to talk about our domain objects rather than ints and strings and other lower level data types. We want to be able to use functions that are relevant for our domain within the database itself. But if you're looking at operations, you still get value from that because you can understand how Postgres is working internally. You can provide new metrics from Postgres that allow you to understand what is actually going on, where it is spending its time, and so on. If you're developing a new platform, you might be interested in specializing how Postgres indexes your data and stores your data so that you can provide the performance that you need. And that can radically change things around. And because finally, and maybe most importantly, because sometimes it allows you to simplify your architecture. This is something that I really care about. Keeping things as simple as possible and not simpler. Sometimes you need to exchange a couple, to have a message queue or something like that. But it's really for a niche use case within your application. You might be able to skip having an external system. If you can just use a small message queue within Postgres itself, you can have Postgres covering some needs that maybe required you to have an external component for that. And that allows you to keep things simpler. There's been a lot of movement in the Postgres space lately, and especially in extensions. Here are a few of the main extensions that are being talked about around, and they range from things that are built as part of Postgres itself, as pgx-rs statements, which allows you to understand what queries are taking the most time, the most resources within your database, going through PostGIS that allows you to use geographical spatial data types and functions within your database, perform searches, having to deal with distances between points within the database itself, and then full-blown products that have been built as Postgres extensions, such as timescale.db or Citus data, which allow you to maybe keep using Postgres and skip having an external time series database such as InfluxDB or things like that. So the there is a lot of movement going on in this area. There is interest, and it is warranted, in my opinion. To build all of these solutions, Postgres gives you a set of tools, a set of extension points that you can leverage. And they go from really simple to quite advanced. On the simpler end of the scale, we find basically user-defined functions. Probably everyone here have seen something like that. You can basically define new functions. They take parameters. They return some kind of type out. And you can write them in SQL or anything like that. And the same mechanism can be used for procedures, which can manage transactions, and for triggers that get invoked as part of the normal usage of your data tables. Then you have custom types, and you can create custom types, again, just in SQL, that map to your domain model. So if you are dealing with colors, you might create a color type and have a color column within your data tables that speaks your domain instead of being 3 different columns mapped to ints or some structure type mapped as JSON or something like that. Or you can create domain types based on a standard type. So you can create a zip code type that is, for all intents and purposes, a string, but will not accept anything that isn't 5 digits. This is just the basics. Then you have the ability to define operators between types, functions that accept these types. You can create aggregate functions that, I don't know, maybe color blend a set of colors and things like that. These are all extension points that are available. You can create new procedural languages. Postgres already allows you to write functions in SQL, function in PLPG-SQL, which is a procedural language built within Postgres itself. But then again, as extensions, you get to write your SQL functions in Perl, in JavaScript, in many other languages, in Python, and so on. And you can, if you're interested in writing, I don't know, SQL functions in COBOL, you can write your own procedural language. Then we go to fairly more advanced extension points. You get access method extension points. Here, there are 2 types, index and table. Index access methods allow you to define new types of indexes for your data. And these require much more than just writing some SQL. But they really give you an edge. One example I cited before is ZomboDB. ZomboDB allows you to use an Elasticsearch instance as a provider of full-text search indexing for a Postgres table. So you get to use your data and integrate full-text search using all the feature set of Elasticsearch without having to deal with that at the application level. It's just moved as an index type within Postgres itself. On the other side, we have table access methods, and these allowed you to customize how Postgres stores the data from your tables. And if you have any familiarity with Redshift, maybe AWS Redshift. So when you do analytics on data, many times what you are doing is a narrow projection of the data they are querying. So maybe you are just calculating the average selling price or the average rating of a set of customers for a product. And your table is very wide, might have 20 columns, but you're only interested in one. So in this type of cases, storing the data not by row but by column allow you, if you're doing this kind of narrow queries, to read a fraction of the total data. And this is possible using a different table access method. Such as in the example they are seeing, it's an example from Citus Data, which provides such an option. And then you have foreign data wrappers. And foreign data wrappers are basically an escape hatch for querying anything through Postgres. And they allow Postgres to see external foreign data sources as if they were normal tables. And external data sources are really anything. So we can look at local files, remote files. We can look at remote APIs that you might want to query. You can query web databases, remote SQL instances, remote Postgres instances, NoSQL databases, anything that comes to mind. You need to write an extension for that. You need to deal with different kind of usage patterns, such as queries, scans, but also insertions and deletions, and you can map those on foreign data. So you can do things like querying the list of EBS volumes on your AWS account in a specific region, filtering them, and all of that directly from SQL. It's a pretty far-fetched example in this case, but there are a lot of interesting use cases for a solution like this, and we'll explore a couple in a few minutes. And then you have many, many more other extension options. You can create background workers that do maintenance on your database. You can customize the inner workings on utility commands in Postgres. You can hook into the planner and understand how Postgres is planning your queries. You can control how Postgres is planning your queries. It gives you a lot of additional options. Extending the functionality of Postgres goes through extensions, which are basically these packages where you put together a set of simple SQL scripts, which might define custom types, custom functions, and so on, but also native code that you use to provide this functionality. All of this gets loaded into a specific database using SQL. So you create extension pg-stat statements, and that gets all of the customizations that you provide as an extension get loaded inside the database, and they have a lifecycle management built in, so you can update with new versions of the extension when the need arises, and you can drop an extension and drop all the related components of the extension itself. Authoring extension can be done in many ways. You can use simple SQL, we've seen an example of that, or procedural languages, but for the most advanced cases, you really need to write native code. And here things get a little bit dicey. So writing native code is basically unavoidable if you want to use the advanced extension points. But then Postgres is developed in C, and you need to write C code. Not exactly, you need to expose functions that use the C calling convention. You need to expose a little bit of metadata out of your native library to allow Postgres to enumerate these functions. But then again, once you do that, you get access to all the inner workings of Postgres. You can do anything that Postgres can do. This can get annoying though. So C is not a high-level language. It's not a language that provides anything in terms of creating safe code, having compile time guarantees that everything will not blow up at runtime. And so basically every time you make a mistake, you get a segmentation fault, your database crashes, your connection drops, and debugging it might not be the most interesting thing to do. You have a very low abstraction level. Your code ends up talking about pointers and offsets, not about the domain that you want to be talking about. You don't have much in terms of composability. C does not provide generics, does not provide templates. And so you have a list of pointers, or you have your custom list every time all over again. And this really, really impacts negatively the expressiveness of the code that you write. It's not fun at all. Lastly, you don't get much in terms of tooling. The tools that you use to write C code, you manage dependencies and such, are basically the same for the last 30 years, and they're nothing that can be compared to what you get with more modern languages. So if you're not interested in writing extensions in C, but you still want to, I don't know, expose something advanced, you want your own type of index, what can you do? There are a few options. I put here a couple of these that are representative. So there are solutions that allow you to, I don't know, for example, multicorn, that allow you to write foreign data wrappers in a higher level language. So for example, in Python, this multicorn, it is really narrower than, it provides a narrow set of features because you can only write foreign data wrappers. And if you are interested in a high level of performance, it might not be the best choice. It being Python, it's not its perfect use case. And you might not like Python. So apart from that, multicorn was active like 6 or 7 years ago, but has not gotten much traction, much movement in the last years. Recently, AWS created trusted language extensions, and they provide something like that. You can write, you can do in SQL and in procedural languages something more than Postgres allows you from the start, but they're not really a solution for this problem. They're more meant to allow you to deploy extensions on managed databases such as RDS, where you don't have access to the file system, you cannot load your own libraries. PostgreSQL documentation itself proposes to use something like C++ to develop extensions. That might be your cup of coffee, or it might not, based on your experience. Today we're talking about something else. Rust has been gaining a lot of popularity in the last couple of years, and I believe deservedly so. It provides the ability to write system level code, so low-level code, native, fast, but with a set of guarantees from the compiler that as long as you write what is defined as safe code, you won't get memory corruption in production at runtime without the compiler pestering you about it at compile time. It provides a high level of abstraction, so you start writing code that talks about your domain rather than pointers and such. It's composable, it has generics, it's a modern programming language. It provides the ability to write code in a functional style, and it has top-notch tooling. Probably the best thing is that it has Cargo, which is a tool that allows you to build your code, to manage your build flags, to manage your dependencies, all in a single package. So this really changes things. It allows you to have a much sharper tool at your disposal. On the other hand, once you go outside of C, you really are left in a difficult situation, because everything from Postgres is exposed as C functions, and to use C functions within Rust, you need to create bindings for that. Postgres provides a set of macros that create and expose your functionality to Postgres, that creates the necessary metadata to allow your function to be used from Postgres, and that you don't have. There is a memory model mismatch. Rust provides you with an ownership and borrow model for memory that really has no mapping with what is being done in Postgres. C does not provide any kind of high-level memory management functionality, and so Postgres created its own. And the Postgres model and the Rust model are completely different, as it would be with C++ or other high-level languages. And the way that Postgres deals with errors, C++ exception, Rust panics, is completely different. And so, again, if you have your code that panics in Rust and propagates an error up the stack, if it gets into Postgres, everything blows up, and vice versa. If you call a Postgres function and it propagates an error, and you call that from Rust, and it reaches Rust by unwinding the stack, everything blows up. So we need something to simplify this kind of interaction. And here comes PGX. PGX, unfortunate name because it's really used in a lot of projects that deal with Postgres. But it is in the context of Rust extensions in Postgres. PGX is a Rust framework that is meant to supercharge the development of extensions in Rust for Postgres. It was developed and open source by TCDI, which is an American company, while developing ZomboDB. It has 3 or 4 years of history on its shoulders. It has an amazingly active, open, and friendly community. It's one of the projects with which I was more happy to work because you have a problem, there's plenty of people trying to help you, and positive feedback loops in integrating your feedback within the new releases of the software. And it provides all of the glue code and of the infrastructure that allows you to bridge those gaps that we mentioned before. It provides you with a framework where you are on Rails, and so you can write functions in Rust. They can take Rust types as arguments. They can return Rust types as return values, and everything gets mapped back and forth to the relevant Postgres types. You can create custom types that are Rust types and then get mapped into Postgres types transparently. It handles by itself the transformation between the Postgres error propagation model and Rust panic handling completely transparently. But then, if you have familiarity with Git, in Git you have the porcelain and the plumbing. So porcelain is the commands that you usually use when you're working, and they are high level and clean, but sometimes you need to get your hands dirty and understand what is going on, debug a particularly difficult situation, do something with a repository that was not meant to be, and you can get to a lower level. And this is the same in PGX, where you can get access to the low-level functions, to the bindings that are provided for Postgres functionality internally. And especially if you are aiming for maximum performance, this becomes something extremely important. Finally, it helps you all the way. So it doesn't just provide the bindings for the functions, the mapping of errors between the two platforms, but it really allows you to download Postgres, build Postgres in different versions so that you can test your extension against Postgres 11, 12, 13, 14, 15, different versions at the same time. It provides scaffolding, so you are starting a new project and you go and you want to create a new extension, and it creates a template for you that you can just immediately test with its own Rust-based test framework. You can deploy locally for testing. It starts a Postgres instance and automatically loads your library within it, really with a couple of commands. And so it takes a lot of the drudgery out of the process. And also, obviously, allows you to package the extension and ship it out so that you have your deployable that you can bring in production or share with others. I'd like you to show just a couple of things that you can do with it, and it will be a challenge since I am with the microphone in my hand. So I'll do my best, or I'll speak very loudly. So in this case, we have my development machine, and what I'm doing is just that I want to create a new extension. So PGX provides you with an extension of cargo that allows you to have specialized commands for creating extensions. So in this case, I go cargo PGX, and then I want to create a new project, and I call it my extension. And at this point, we get inside the folder, and we see a complete Rust project with a cargo YAML file where we have libraries, build profiles, dependencies, and all of that already provided. We have a myExtension.control file that defines how my extension needs metadata for the extension the Postgres needs. And in the source folder, I get a single file, which I can get a peek inside, that provide, in this case, a demo function, which is hello my extension, which in this case returns a string, and it's just Rust code. And also, speaking about that, I have a test that is defined, which asserts that when I call hello my extension, I get back the string that I'm expecting. So at this point, I want to test out my okay. Wrong folder. I want to test out okay, sorry. Network. The Wi-Fi router disabled itself because it was fun for me to flail around. Okay, and so now it's building the. Let me speed it up for you just a little while so that we don't waste our time here. Okay, so now it builds my extension, and since I launched it with the Cargo PGX run, it will start a Postgres instance. It will deploy my extension within it, and I will get the ability to call the Rust code that it provided for me directly from PostgreSQL. It is not without defects. One, if you are working with Rust, Rust compiles pretty slowly, and PGX is a complex piece of software. So the first compilation is a little bit time-consuming, maybe a minute or so. It supports, obviously, incremental compilation, so subsequent runs are basically instant, and we'll see about that. So here, it did what it needed to do. It started the Postgres instance, Postgres version 13, on a temporary port. At this point, I can create my extension. Okay, I created it before. Drop extension, my extension. I create my extension, and now I can select hello, my extension. Underwhelming. So let's see something that is more interesting. In this case, let me go here. Maybe you deal with fiscal codes in Italy. So you have a library which has been developed and open sourced by someone, and it's available, and it allows you to validate fiscal codes and get metadata out of fiscal codes. You can provide an isValid fiscal code function, which takes a string. This accepts any type, text-like type from Postgres, and returns a Boolean. And it just applies the function codice fiscale check, and whether it fails or it works correctly. Or maybe you are dealing with emojis. You have some kind of platform where that is relevant, and you want to create emojis by their name, so smiley, rocket, or anything like that. And you can use an emoji library. Again, you take the name of the emoji that you want to load, you pass it on, and you yield the emoji instead of the name of the emoji. Or you want, again, set returning function. You can have functions that return record sets. And so in this case, I can enumerate all the emojis that are managed by the library itself. Or I might be interested in defining a new type. Let's suppose that I have a URL type. I want to talk about URLs within my application. I create a URL type. It has two parts, a scheme and a host. And I provide, by implementing simple interfaces, traits that PGX gives me, the ability of reading and converting between text and URL back and forth. And then I can create functions such as isSecure that verifies if the scheme of my URL is secure or not. And all of this is available from within, from my extension. And so if I go inside ed and cargo pgx run. In this case, let's say I use something like that, or I want to select star from list emojis. Maybe offset 100, limit 10. And it's something that really, or I want to know if it's secure, and I say HTTPS. But if it is HTTP, that's not secure, something like that. But then, more importantly, we can build something like I showed you before. So I want to enumerate my EBS volumes from within Postgres itself. And so in this case, I've created another extension. This extension, we can look at that. It's 100 lines of code or something like that. It took a whole of half an hour to write. And now what I can do is that I can go here. Create the extension, create a foreign data wrapper, which is called EBS. I can create a server which connects to my AWS account by using my credentials. And I can create a foreign table which maps to the EBS volumes within my account. At this point, I can select star from EBS volumes. And I can basically filter them, only the encrypted ones, or I can do something like how much space I'm using for encrypted volumes on AWS. So why is this relevant? Yeah, thank you. So why is this relevant? We've been able to use this for a project that we have worked on last year. We had a distributed system that was processing large amounts of data stored in a proprietary format from historical reasons from one of our clients, customers. And it had a proprietary query engine. So if you wanted to query this data, you had to use its own language, its own constructs and such. And it really made that difficult to work with. Basically, you had to learn a whole new query mechanism that was specific to this platform. It was expensive to maintain and extend, and basically offered a fraction of what Postgres can do. What we did was that we re-implemented the query engine as a foreign data wrapper, and so we exposed to all the proprietary format data, from this platform to Postgres, and we queried that through Postgres. So we could use standard drivers, like the JDBC drivers from Java or anything like that, to query the data. And we did something that was quite advanced. You can do parallel scans, and so the data was compressed, and we could use 56 concurrent threads to decompress the data in parallel and process that. You can do predicate pushdown, and so basically in the example that I showed you earlier, when I'm querying the volumes from EBS, I'm requesting only the encrypted ones. And this, the clause where encrypted equals true, is pushed to AWS. And so I do not get down 100 volumes just to filter out 3. I just get the 3. Super fast, 500 million rows per second, 90 gigabytes of decompressed data per second on a single node. It was far easier to access that data. Anybody that had a SQL experience could do that. And it was far cheaper to maintain, because now we just needed to provide the glue between Postgres and the rest. So this is the kind of work that we do in Option Factory. I hope that you find this interesting. I'll be available all day if anybody wants to have a chat about that or is curious about something of this, see something more that we haven't had time to discuss today. Get in touch if you're interested. And thanks for your time.
Okay. Thanks a lot, Francesco. There's not time for questions, so again, you will be around, so please ask him later.